Alright, so in this video we go over section 9.1 polar coordinates. Well, so in this case we introduce a new coordinate system called polar coordinates, in which, as opposed to the original x, y plane, or the rectangular coordinate system in which a point gets plotted by x comma y. X is the horizontal direction and y is the vertical direction. So in this new system, we are going to plot a point in which the x coordinate becomes the radius and the y coordinate becomes the angle. In a way, a good way to see this is, well, consider like plotting this xy point as a bird's eye view, like seeing it in the top, in which we would look at the radius and the angle. So let's see, so here the r is the distance from the pole. Actually, the origin is called the pole, and then the x-axis is the polar axis. So a point r theta, an arbitrary point, is going to have a radius r, and it's going to extend to an angle theta. Alright, so let's do some examples so we can have a good visual of what these points are. Well, so number one, the graphs are going to look a little bit different. They're going to look circular, and then in this case each circle right here will represent 1 unit in the radius. And in this case also we are going to, okay, let me actually mark this as the axis. And then, well, so we're gonna plot the point 3, 6, which is the radius equals 3 and the angle is 60 degrees. So we're gonna go 60 degrees, which is roughly here. Okay, so I'm gonna go with the angle 60 degrees, which is gonna be this one, and the radius is gonna be 3 units. So that's 1 unit, 2 units, 3 units. So that's the point 3, 60 degrees. Now, keep in mind that the fact that the points, the angles are periodic, these representations are not unique. So that's why we can express this in different ways. So for example, another way to see it, if we add 2 pi one more rotation, another way to say this is, well, 3, 420 degrees. And that's if we do another rotation, And then another way, which is a little bit tricky to understand at the beginning, well, we could go in the negative direction, like this. Let me use a different color and extend this like this. All right, and then in this case the angle that gets extended is 240 degrees. Well, let me actually, not in this direction, but actually in this direction, the angle is 240 degrees. But in this case, notice the point is not in the same quadrant as it is the original one. So what we do is move this point to the other side. But we're changing the sign of the radius, because if we move it over here, we would be changing the sign of the radius. Let's do another example, one involving radians this time. So pi over 6 is this angle right here, but in this case the radius that we want is just 2 units. So in this case we're gonna go 1 unit, 2 units, and that's okay. Let's do this 3, 6, actually pi over 6. That's the angle that goes. All right, so in this case that's the point 2, pi over 6. Okay, so let's represent this angle in a different way. Well, number one, if this angle gets, if I do one whole rotation, like from here, add 2 pi to get there, I would get, in this case, 17 pi over 6. And the same radius. Another way is to go, in this case, extend it over here. All right, but the angle from here to there would be a 5 pi over 6 with a radius of 3. However, the location is not the same as this one right here. So if we change the design to the radius, we can have it back to the first quadrant. So we need to express this one as a negative 3 comma 5 pi over 6. Let's do one last example. So radius 3, angle 3 pi over 4. 3 pi over 4, by the way, is in the second quadrant. It's actually 135 degrees over here, and a radius of 3. So that's the angle 3 pi over 4. And that's where we 3 comma 3 pi over 4. Okay, so number one, let's do a whole rotation from here to get to the same point. Well, in this case, I'm running out of space here. I'm going to write this below. So we're going to have the same radius 3, and what else? And what happens here is the angle becomes 11 pi over 4. So if you add one rotation, that is add 2 pi to this angle, so 2 times 4, that's 8, plus 3, that's 11 pi over 4. Of course, we can do the negative version of it, so like going in this direction. All right, and then, well, in this case, that'll be what do I have? Well, if I go all the way from 0 to this angle right here, the angle would be 7 pi over 4. But notice the radius over here is the opposite to that radius, so in order to bring it back, we need to change this sign. So, as opposed to rectangular coordinates, well, polar coordinates representations are not unique. That's what we want to say here. When you have the point, I don't know, 3 comma 3, well, 3 comma 3, it's unique 3 comma 3. In this case, there's no rotations, there's no periodic functions at all. And in this case, well, there's trigonometry involved, there's circular points. Well, these are not unique. So as far as having the negative signs, well, let's have a look at this definition right here. Well, so we have these two points. Well, this 2 pi k right here telling us that these points are not unique, because we can add multiples of 2 pi to the angle having the same radius. And if we change the sign of the radius, well, notice we always added that pi. See what we did? Let me go back to the example. So when I change the sign, we added pi to it. All right, so basically we move it 180 degrees. Now there has to be a way to go from one system to the other system. Well, if P is a point with polar coordinates, the rectangular coordinates x, y are given by, well, so x equals r cosine theta, y equals r sine theta, and these come from, for example, that's the point x comma y that goes from the origin to the point with a radius r. So this is x, this is y. Using trigonometry, well, cosine theta equals adjacent over hypotenuse, that's x over r, and sine theta equals opposite over hypotenuse, that's y over r. And then from here, solve for x to get r cosine theta, solve for y to get r sine theta. So we can always relate this to the triangular relationship of the trigonometric functions to polar coordinates. Okay, find the rectangular coordinates of the points with the following polar coordinates. Well, so we want to find x and y. So we go from r theta to x, y. So in this case, r cos theta, r sine theta. And all we do, this is very, very formulaic. It's going to be, say, 6 times cosine of pi over 6 and 6 times sine pi over 6. All right. And well, we use the unit circle, of course, to change these coordinates. Well, cosine of pi over 6, that's square root of 3 over 2. And sine of pi over 6, that's 1/2. And in this case, 6 divided by 2, that's a 3 root of 3. And 6 divided by 2 is 3. 3 times 1 equals to 3. In other words, 6 comma pi over 6 is equivalent to, say, 3 root of 3 comma 3. All right. And it's worth to mention that this point is in the first quadrant. It matters. You'll see why in a second. So the signs have to match. An angle of pi over 6 is in the first quadrant, and a radius, well, doesn't matter the radius, it's still going to be in the first quadrant. Let's do letter B. Letter B, well, let's find x equals r cos theta and y equals r sine theta. So in this case, well, the radius is -4 cosine of negative pi over 4. Okay, before evaluating the quantities here, let's first of all investigate what's the location of that point. First of all, be careful, this could be a little bit tricky. So an angle of negative pi over 4, that lies in the fourth quadrant, all right? So that's a negative pi over 4, that's in the fourth quadrant with a radius of 1, 2, 3, and 4, all right? It's going to be right here, actually. However, look at the sign of the radius. The sign is negative, so in this case, because of the sign having the radius having the opposite sign, we're going to go 1, 2, 3, and 4 in the opposite direction. So ultimately, this will be in the second quadrant. All right. So let's go about do the calculations. Cosine of negative pi over 4. If you remember, cosine is an even function, so cosine of a negative angle, it's just the negative sign just disappears. And in this case, well, cosine of pi over 4, so -4, that's root of 2 over 2, which is 4 over 2, that's a -2 root of 2. And then over here, sine of a negative angle, the negative sign goes outside, making this a positive quantity, because negative times the negative that it's outside. And in this case, that's 4 root of 2 over 2. And that's a 2 root of 2. And if we write this point, well, that's a -2 root of 2, comma 2 root of 2. Negative x, positive y, isn't that the second quadrant? If you say yes, well, of course, yes it is. Okay, now how do we go from rectangular to polar? Well, that's going to be a little bit different because we're going to have some restrictions here. So number one, always plot the point in the xy coordinate first. So the quadrant is going to matter. So that's why we want to plot the point in the corresponding quadrant. Well, so to find the radius, use the formula r equals x squared plus y squared, because ultimately, you know, that's the point y. So we want to find the radius using basically the Pythagorean theorem, x squared plus y squared equals r squared. And then, well, r equals the square root of the sum of the squares of x and y. All right. And then for the angle, well, keep in mind that from trigonometry as well, but let me actually do another drawing here. Would be better. So in this case, what do we have? Well, so I have a radius, and that's y, that's our x. Well, if we're looking for the angle between the polar axis and the point, well, the angle that relates y and x is tangent theta equals y over x, and therefore theta is inverse tangent of y over x. However, this is true only when our points are either in quadrant 1 or quadrant 4, and you might remember that from inverse trigonometric functions, you know that the inverse tangent lies only in between these two quadrants, right, in quadrant 1 and 2. And then when we had a point that was outside, remember we move it one way or another to either quadrant 1 or 4. So basically what we did is simply add pi, but in that, when we covered inverse trigonometric functions, I didn't just wanted to say that we added pi. I wanted to explain that, well, it has to do with the signs of the quadrant in which the given point is. So in this case, now we can safely say that we just add pi if our point lies in the second quadrant or the third quadrant. Otherwise, quadrants 1 or 4, just arctan y over x. Alright, let's go over some examples of how to convert points that are given in the polar coordinates, to, in this case, what's it called? Are given in rectangular and change them to polar. Alright, so that's going to become something, comma, something. We'll find out. So number 1, we need to find the radius r equals the square root of 2 squared plus negative 2 squared, which in this case is the square root of 4 plus 4, which is 8, which reduces to 2 square root of 2. Alright. And by the way, which quadrant is this point at? This is the point 2, negative 2. Alright, we will find out. And then that's 4 quadrant. 4 quadrant, so adding the pi is not going to be necessary in this case. So theta simply tangent negative 1 of y over x. Alright, y over x, and then in this case tangent inverse of 2 over negative 2. Actually negative 2 over positive 2. And well, in this case we're looking for tangent inverse of negative 1, which in this case, due to the quadrant that is being in quadrant 4, that's a negative pi over 4. Alright, so the point is going to be 2 root of 2 negative pi over 4. Alright, and that's indeed going down to negative pi over 4 with a radius of 2 root of 2. That's a 4th quadrant. Let's do another example, letter B. This one is going to be a pretty interesting one. So let's see. So number 1, the radius, it's going to be negative 1 squared plus the square root of 3 squared, which in this case cancel. That's a negative 1 squared. That's 1 plus 3, which equals a 4 inside of the radical. That's a 2. So the radius is 2. And then the angle in this case, well, let's find out first of all the location of this point. I'm going to put it up here. That's going to be negative 1 comma root of 3. So it's in the 3rd quadrant. In this case, we will need to actually add pi to our angle. So pi plus tangent inverse of y over x, and then in this case pi plus tangent inverse of y over x, that's root of 3 over -1. Well, this one might be a little bit tricky to, when it comes to inverse tangent. So I'm going to rewrite this as pi plus tangent inverse of, that's a square root of 3 over 2 and -1/2. So the point in the unit circle where y equals root of 3 over 2 and x equals -1/2, in this case is 2 pi over 3. Right? Now we need to combine these two, these two angles. So in this case, what are we going to have? Well, so that's 3 and 3. That's 3 plus 2. That's 5 pi over 3. And 5 pi over 3, if you notice, it's indeed in the third quadrant, actually. All right. Oh, wait a minute. No, that's hold on. That's second quadrant. That's second quadrant. No, never mind. Yeah, that's 5 pi over 3. Yes, that's correct. So this point will be then, instead of -1 comma root of 3, that's the radius is 2 and the angle 5 pi over 3. All right. Final answer to this one. Okay, another thing that we do with is to transform equations between polar and rectangular forms. So in this case, we are going to write a function that is given as function r of r equals some function of theta, and then we are going to convert that into one that looks like y equals some f of x. All right. Okay, let's start with r equals to 5. Well, r equals to 5 means radius equals 5. Well, when you think of radius, well, we think of a circle. So we're looking for a circle of radius 5. But now, how do we express that algebraically? Well, from the previous page, keep in mind that r equals x squared, the square root of x squared plus y squared in the rectangular system. So what we have to do in this case is simply replace r with the square root of x squared plus y squared, and that equals to 5. And then to solve this equation, well, not rather to solve, because it will be an implicit. X squared plus y squared equals 5 squared, which is 25. And if we recognize this is the equation of the circle with center at the origin, it has a radius 5. All right. Okay, let me leave b to the end, because that's one is going to be an interesting one. So let me do r equals 3 cosecant theta. Well, every time you have functions, or actually equations that have like a tangent, cotangent, secant, and cosecant, a good way to go about this is to write these cosecants in terms of sines or cosines. So in this case, r equals to 3 over sine theta. All right, and then I'm going to multiply both sides by sine to get r sine theta equals to 3. But what do we know about r sine theta? R sine theta ultimately is it's y. Y equals to 3, and that's the final answer. Ultimately, this r equals 3 cosecant theta represents the horizontal line y equals to 3. And let's do one more. Well, r equals -6 cosine theta. Well, what about this one? So So one thing that when you have sines and cosines, you're looking for two things. Number one, you're looking for r cos theta to transform that into x, or you're looking for r sine equals theta to turn that into y. In this case, well, we have the cosine only. We don't have the r. Can we multiply both sides by r? Of course, we can do that. And yes, in this case, we can multiply by r even though it could potentially be 0. But in this case, it's not 0 because we're talking about a radius, and the radius cannot be 0. So that's going to become r squared equals minus or negative 6 arc cosine theta. So on the one hand, this quantity becomes x, and this quantity becomes the sum x squared plus y squared. So let's go ahead and do that. So x squared plus y squared equals negative 6x. And we are essentially done with the conversion, but we might want to go the extra mile. I'm going to add the 6x to the other side, or to both sides actually, to move it to x squared minus 6x. And I'm going to leave a space here, plus blank plus y squared equals to 0. But because I'm adding a blank, I have to add the blank to the other side of the equation as well. But what are those blanks for? Well, in this case, if you're thinking of completing the square, that is correct. So to complete the square, we divide the coefficient of x to the first power by 2 and then square that number. In this case, negative 6 quantity divided by 2, that's a negative 3. And the negative 3 squared equals to 9, positive 9, positive 9. All right. So that's what it's going to represent here. And in this case, well, this will be a perfect square trinomial which factors like x minus 3 squared plus y squared equals 0 plus 9, which is 9. And then in this case, we have another circle here, a circle of radius 3 and center at a point 3, 0. Right? Okay, let's look at this one right here. Well, for letter B that we have theta only, well, what can we do about it? We don't even have a trigonometric function to begin with. That's a big problem here. However, we could just introduce we can introduce a trigonometric function. In this case, the easiest one. Well, I know it's not necessarily the easiest one. I'll tell you why it's the easiest. I'm going to take tangent on both sides. Tangent theta. Well, tangent of pi over 4 is 1. But in terms of the angle, tangent theta, yes, if we go back up to the previous page, what is tangent theta? Y over x. So this is the trick to turn a theta into y over x. All right? So let's see. Tangent theta equals y over x, and multiply both sides by x, y equals x. All right, how are these two related? Well, so if you think about it, the line y equals x is simply the diagonal line. All right. Now, if we ask ourselves what is the angle from the x-axis to the line, isn't that 45 degrees or pi over 4? Of course it is. So that's how these are related, in a geometric or a visual way when we change these two equations in one system to another system. Okay, example 5, transform each equation from rectangular coordinates to polar coordinates. So in this case, we want to do the following. We want a function y equals f of x and transform that into a function r that depends on the angle theta. All right, so number one, so the tools that you want to use here are only that x equals r cosine theta and y equals r sine theta, amongst other algebraic techniques that we're going to use here. So replace x with r cosine theta, replace y with r sine theta. So 2 times r cos theta plus 3 times r sine theta equals to 5. Okay, so we want to solve for r in this case. Notice r here is a GCF. It's a common factor. So that's an r times 2 cosine theta plus 3 sine theta equals to 5. And dividing both sides by this quantity, we get r equals this whole quantity in the denominator and a 5 in the numerator, and final answer here. All right. Now let's go about the second example. Let's go about the second example. Well, so 6xy equals to 7. So 6 times x, which is arc cos theta, times y, which is r sine theta, equals to 7. And I mean, we're essentially done pretty much with this equation, but we can simplify a bit further. Number one, r times r is r squared. And I'm going to factor out the number 6 as 3 times 2 cosine theta sine theta. All right. And then in this case, well, that side equals to 7. And, well, you might recognize this as an identity. This is actually sine up to theta. Then 3r squared sine 2 theta equals to 7. And in this case, this is typically the final answer that you want to leave at the very end. And the reason why we're not solving for r is because in this case r has a power of 2. And then in that case we would need to use the square root property, giving us a positive and a negative answer. You don't want to have that. However, we can further solve for r squared only. So r squared, oops, actually r squared equals to 7 over 3 sine 2 theta. All right, 7 over 3 sine 2 theta. And in this case, you might want to use identities to move the sign to the numerator and have this r squared equals 7/3 of cosecant 2 theta. All right. Let's do one more. Well, the first thing you want to do here is replace x with r cos theta and y with r sine theta. So let's see. Arc cosine theta minus 1 quantity squared plus r sine theta, the whole quantity squared, equals to 1. All right, and I'm just replacing y with r sine theta, x with r cos theta. Over here, we're going to have a binomial squared. So the binomial squared, again, is the square root of the first term, and in this case, minus 2 times the first term times the second, and plus the square root of the second term. In other words, r squared cosine theta, actually cosine squared, because this square, when we square the first term, affects both the radius and the trigonometric function, and then plus 2 times arc cos theta times 1, well, I'm not going to write that 1, and then plus r squared sine squared theta equals to 1. Alright, oh, actually I forgot to square the 1. That's there's a plus 1 over here I didn't write. Alright, so in the next step, what am I going to do here? Well, I'm going to put these two together because we have a positive sine squared and a positive cosine squared. You'll see how's that going to be useful. R squared sine squared theta plus r squared cosine squared theta plus 2r cos theta plus 1 equals to 1. And what's going to happen here? Notice how these ones go away. Alright, giving us, so those are going to give us a 0 and a 0 here, but what we want to do here, we're going to factor this r squared to r cos theta equals to 0. And this is an identity. Sine squared plus cosine squared, isn't that equals to 1? Yes, it is. So r squared times 1, it's going to be r squared plus 2 times, well, actually this is supposed to be negative, not positive. Negative, and then negative minus 2 arc cosine theta equals to 0. So in this case, we are going to solve using the in this case, there's a couple of ways to interpret this well. So r squared equals 2r cosine theta. And in this case, we can safely divide by the radius, or actually by r, because really the radius is never 0. And actually, r is a good solution to the equation because, 0 minus 1 squared, that's positive 1, plus 0 squared, which is 0, that's 1 plus 0, which is 1 equals 1. So it satisfies the equation, and ultimately r equals to 2 cosine theta. And that's our final answer over here. And this is the end of this section. It's a good place to quit. I'll see you in the next video.